Anyway, let's get into it. Now, first we need a little review of percent composition so that we can use that information to figure out what the formula of a compound is. So we've done this before. We did it a lot in our lab. Percent by mass is the mass of an element in 1 mole of compound over the molar mass of another compound. It's part over whole. So let's just review the idea of percent. Enjoy this little video.
In this demonstration, we're going to calculate the amount of a component in a commercially available product. Here we have some bubble gum, and the first item on the list of ingredients is sugar, indicating that that's the component that is present in the larger amount. How much is present? In order to determine that, we're going to take 5 unwrapped pieces of the bubble gum and mass it in the cup that we have here on the balance. We recorded the mass of our cup. Now we can record the mass of our cup and chewing gum. And now we'll chew it for about 5 minutes to remove all of the sugar. Our 5 volunteers have completed chewing the gum for 5 minutes, and we've collected the gum in the paper cup. Now we mass it. Now we're able to take the data of our mass of the gum before the reaction and after chewing and compute the percent of sugar. To go through the calculations of this demonstration, we find that we began with 41.83 grams of the chewing gum in the cup. Subtracting the mass of the cup, we began with 40 grams of the dry gum. We then chewed the gum for 5 minutes, and after chewing, we massed it and the cup. Subtracting the mass of the cup, we had 12.62 grams of the gum without the sugar. Subtracting the mass of the gum without the sugar from the gum with the sugar, we found that we had 27.39 grams of sugar in the 5 pieces of chewing gum. Placing that mass of 27.39 grams of sugar over the mass of the gum before we started, 40.01 grams, we can calculate the percent of 68.45% sugar in the chewing gum.
All right, I'm sure that was 100% clear, but we're going to practice anyway. So, if we have a compound such as Na2CO3, sodium carbonate, let's figure out what percent each element is of the molecule. Now, we're going to assume we have 1 mole because that's easier because the mass numbers are on the periodic table and we need mass. So, for percent sodium, we would take 2, which comes from the formula. There's 2 sodiums in the compound. 2 times the mass from the periodic table, divided by the mass of the whole compound, the molar mass, the 2 sodiums plus a carbon plus 3 oxygens, times 100%. It gives us 43.4% sodium. Carbon is going to be 12 over the 106 times 100 because there's only 1 carbon involved. That gives us 11.3% carbon. The oxygen, there's 3 of them, times 16 over 106 times 100% gives you 45.3%. We could have found that by difference also because these 3 numbers should all add up to 100%. So if we knew the first 2, we could subtract from 100 to get the last one. All right, moving on. Now here's the meat of the matter. The empirical formula is the simplest whole number ratio of atoms in a compound. For instance, hydrogen oxide, hydrogen dioxide is H2O. The empirical formula of water is, whoops, I hate when I do that, H2O. It's the simplest formula. It's not H4O2 or H6O12. It's the simplest ratio of the elements. Now there is something else called a molecular formula, but we'll get to that next time. Let's try determining the empirical formula from a percent composition. So let's say we have a compound and we were able to break it apart and find out that it has 38.43% manganese, 16.80% carbon, and 44.77% oxygen. We can figure out the formula from that compound. Now, percent always means part of 100. So if we also assume that we have 100 grams of the compound, then we can have mass of each element by using their percents. So out of 100 grams, we would have 38.43 grams of manganese out of 100 grams of the whole substance, because it's a percent. Now here's what we're going to do with that. We're going to find the grams the way we just talked about, just changing the percent to a gram. We're going to find the moles of each element using their molar mass, something we've been doing a lot of lately. We're going to find the smallest whole number ratio of those moles, and that will give us a formula. Sometimes we'll get a fraction and we'll have to multiply it to get a whole number. All right, let's dig in. So for manganese, we're going to find the number of moles, and we would do that by knowing its molar mass of 54.938 grams. Take the grams times the ratio of 1 mole over 54.938 grams, and we find the moles of manganese. We're going to do the same thing for the other elements. Carbon, 16.80 grams, divided by its molar mass is 1.399 moles of carbon. And oxygen, 44.77 grams, changed to moles, gives you 2.798 moles of oxygen. Pause if you need to get this work copied down, and we'll be right and come right back. Okay, the results show that we have a mole ratio of manganese to carbon to oxygen of 0.6995 manganese to 1.399 carbon to 2.798 oxygens. That is not a very obvious way to get a ratio. So we need to divide each of those by the smallest number so that we can get whole numbers. So here's how we do that. We take 0.6995, which is the smallest, and divide it by itself. So we say, okay, for every 1 mole of manganese, we'd get 2 moles of carbon. I just took the moles of carbon that we had and divided it by that smallest number. Moles of oxygen, 2.798 divided by 0.6995. Can you guess what that is? A nice even 4. So now we have a whole number ratio of 1 manganese to 2 carbons to 4 oxygens. Can you guess what the compound formula is? If you guessed MnC2O4, you are correct, because we found the ratio by mole of manganese, carbon, and oxygen. That is called the empirical formula. Let's try another one. Okay, here we have a 9.2 gram sample of a compound. We have 30.4% nitrogen and 69.6% oxygen. We can use these percent compositions. We could figure out how many grams are in this sample, but what's easier is just using these percentages as grams. Remember, we can assume we have a 100 gram sample. So if we assume we have 30.4 grams of nitrogen and 69.6 grams of oxygen. Pause, take a moment, and see if you can figure out how many moles of each element there is. Come back when you're ready. Okay, to figure out moles, we need to divide by the molar mass. And nitrogen, that's 14.0, and that gives us a number, which is 2.17 moles. Okay, for oxygen, it's 1 mole, 16 grams. Sorry, it's kind of hard to write without seeing where you're writing. .35 moles. Okay, so you might be able to see the ratio here, but to make sure it's really obvious, now we divide both of these moles by the smallest one. So 2.17 divided by 2.17 gives you 1 mole of nitrogen for every 4.35 divided by 2.17, which equals 2 moles of oxygen. So our answer is NO2, 1 N to 2 O's. Now your numbers may not come out exactly on a whole number. It may be 1.99 to 1. That's okay to round that to a whole number. There are times, however, when you can't round. When you get a ratio that is 1.5 to 1, you might need to multiply that in order to get a whole number. If you get a 1.5 to 1 ratio, what whole number is that? What can you multiply by? That should be a 3 to 2 ratio, right? You multiply both of them by a 2. What if you get a 1.33 to 1 ratio? Hopefully you'll see that that's a 4 to 3 ratio. If you multiply both of these by 3, you'll get a whole number. Look to see what fraction the decimal is, and that should guide you to what you need to do to multiply it to get a whole number. What about 1.25 to 1? Multiply by 4, and you get 5 to 4. I think you get the idea. We'll practice some of these on your own. Fill out the summary form, and we'll see you next time. Bye.